Hello, good morning, good evening, whenever you're looking at this video. I hope you are doing well. We are going to start on chapter 4, so without further ado, I will get to it. Okay, let me share that screen with you and put it on a slideshow. Here we go. Okay, well, today we are going to start on chapter 4. Now, when you're reading chapter 4, make sure you only are doing the 4.2 and 4.3. We won't be covering 4.1. We're just going to do those two, 4.2 and 4.3. So let's get on to it and take a look at those objectives. So for chapter 4, we're going to describe the development of the brain and the effects of experience on development. Then we're going to describe typical types of brain damage. And then finally describe possible ways to recover from damage. Only 3 objectives in this section, but they're kind of long, so we'll see how it goes. But I think as chapters go, chapter 4 is a pretty reasonable one. So let's move along. So the first thing we're going to do is describe the development of the brain and its effects, the effects of experience on development. The brain starts, or the nervous system in general, you start out as a multi-celled organism. You really don't even have a brain, you don't have a heart, you don't have anything, right? So right after conception, the nervous system starts to develop very rapidly, and it starts with something we call the neural tube. And that will eventually, one side of it will kind of flower out and become the brain, and the rest of it will become the spinal cord. And so let's take a look at that. The neural plate, it starts with the neural plate, and then the plate starts to kind of fold in on itself, and it makes a tube in the middle, and that tube will eventually become the central canal of the spinal cord and then the ventricles in the brain. And so let's take a look at what that looks like as the baby develops the brain. So here you start with the so this is 3 weeks. So this is 3 weeks after conception. So you haven't got a whole lot, but you're in this embryonic stage, and your organs have started to develop, and your brain has started to develop. And there you can see the spinal cord, and it's kind of this elongated neural tube that gets kind of thicker at the bottom. Notice how big the midbrain is, though, relative to the forebrain and the hindbrain. It's, eventually the forebrain is going to become huge, as you see at birth, but it gets bigger over time. You can see kind of the development there at 7 weeks, and it's at 7 weeks when we start to develop genitals and stuff like that, and other organs. And then at 11 weeks now we have some what looks more to us like a brain, but it doesn't have all that convoluted pattern that the cortex normally gets. And then at birth, the brain actually looks like an adult. So it reaches that adult level pretty quickly. If you look at these at the very bottom there, you see the size of the brain. At 1 year old, the brain is almost as big as an adult. So the brain does develop fairly early in life. But some of that development happens after birth, and we'll see that. Okay. So what happens in that development process when the baby is in utero and then afterwards? Well, initially, we just need a lot of new cells, and that we call proliferation. So that just means, proliferate means build a lot more. And so we get a lot of production of new cells. Mostly that's happening in utero, but it also happens after birth as well. And the cells are born in the ventricles. But then they've got to move to different locations. So if it's a cell of the cerebellum, a cell's got to move in that direction toward the cerebellum. If it's a cell of the pons or the medulla or the, let's say, the motor cortex, it's got to move there. And it does that in a process called migration. And in that process, the cell kind of knows where to go through the use of chemical guides. So there's chemicals that are sort of attracting the cell to moving over there. And then once the cell gets over there, because they're really still stem cells, they really don't even look like neurons. And once the cell gets over there, we start to see differentiation where they start to look different from, any other cell. And that's the formation of axons and dendrites. Finally, synaptogenesis. Genesis means the beginning. So the beginning of synapses, and that's where you start to see these neurons kind of hooking up with one another. And that's going to happen. That actually happens throughout life. That's happening in your brain right now as you're learning things. Synapses are forming and working better with one another. It occurs throughout life, but it mostly occurs when you're young. And then myelination is just the growth of myelin along the axons, and that is formed by glial cells. If you remember, in the first chapter, the glial cells are in the brain and spinal cord are the oligodendrocytes, and then in the peripheral nervous system, they're the Schwann cells. And the myelin is going to continue growing even in adulthood. We do get myelin growth as well. So some of these happen early, some happen a little bit later. Okay, well, we used to believe, and this is what I say old school, because when I was in school, they taught us that after infancy, there were no new neurons. So all you did was basically lose neurons your whole life. And what we found now is something a little bit different. We have found stem cells, these baby cells that haven't differentiated yet, in various parts of the brain. We see them in the hippocampus and the olfactory receptors, and they do divide and migrate and become new cells throughout life. So we do get some formation of new cells, but certainly not at the rate that we do as a baby, and not in the cortex. Unless some brain damage has occurred. And even then, we don't see the recovery from damage being associated with those new cells very much. So we get some new cells, but we haven't really learned how to harness that into recovery from brain damage, basically. Our bodies don't recover from brain damage very well, and we'll talk about that in this chapter. So as I mentioned, how do growing cells know where to send their axons? So they're sending out an axon. That axon is going to connect. So, for example, let's say, remember that some of your visual neurons are going to connect to the thalamus, and from there, that's going to connect to the occipital lobe. As they're sending out those axons, how do they know how to connect? Well, there are chemicals coming from the thalamus that those axons growing from the eyes are attracted to, and then there are chemicals coming from the occipital cortex that axons from the thalamus are attracted to, same. So basically the target sort of attracts the growing axon and gets it going in that direction. Okay, well, let's talk about neuron survival, because when you are born, you have way more neurons than you're going to have in adulthood. And they're overproduced by about 50%. So you're going to have a lot of neurons dying. And so you may say, well, why would our brains even do this? Why would they overproduce neurons so much? And what it comes down to is they want to see your brain wants to see what the world is like when you get out of your mom. And the neurons that you lose have a lot to do with what your world is like. So we'll talk about that in a minute, talk about experience. But first, let's talk about neurotropins. Neurotropins are chemicals that are released with the neurotransmitter. They're not neurotransmitters, but they're similar chemicals that are released with the neurotransmitter during an action potential. And what happens when you're a baby is that if you have these neurotropins, that sustains the connection between those two neurons, because this neuron fires, it sends off neurotransmitters, but it also sends off neurotropins. That sustains the connection between these two neurons. So if that doesn't happen, and if this guy does not receive neurotropins, he dies. And then that's sort of how it happens. We call that apoptosis. And that is the death of a neuron. We say sometimes it's programmed cell death, because if it's not getting those neurotropins, it's going to die. And that's it. So it turns out that experience is going to drive that, and we'll talk about that. So neural competition or neural Darwinism is this idea of the survival of the fittest. The ones that are getting use, the synapses that are getting use, are the ones that get stronger. The others die. through apoptosis. So what it comes down to is, if let's say your motor neurons are getting a lot of activity, right, they're going to stay really good. And if they're not, they're going to tend to die out. So if you're, let's say neurons for hearing are getting a lot of activity, they're getting a lot of use, they're going to be sustained. If not, they'll die out. And one of the things we'll see is that, for example, babies that are born blind, many of those connections that are necessary for vision just die out because they're just not getting the experience. As it turns out, that it's very important for children to get a variety of experiences. And this is why the American Pediatric Association would say, do not put your baby under 2 years old in front of a screen, no screen at all, no iPad, no television or anything like that, because the stimulation is too low. And when the stimulation is too low, the baby will start to lose brain cells. And again, we're not very good at producing those later in life. So if you lose them early in life, you may be limited. Physical activity is extremely important for the developing brain, extremely important. And also the aging brain, where we're again losing neurons again. Physical activity seems to sustain those connections very well, because when you're doing physical activity, you're getting a lot of stimulation. So that's extremely important for children, and really a terrible crisis right now, because many children are not getting enough physical activity because of all the screen time. Okay. The input to the brain determines the structure of the brain. As I was mentioning before, if you're born blind, your occipital lobe will not respond to visual information. Those connections to the eyes die away. Now, what happens is, if the baby gets a lot of auditory stimulation, then some of those areas, like the occipital lobe, where it normally would respond to visual stuff, starts responding to auditory stuff. But specialized training of children, for example, if you train your child to do a Rubik's Cube, or if you train your child in, violin playing or something like that, or how to play guitar, drums, whatever, train your child how to dance, then the areas that are involved in that activity will tend to get stronger. And we see that with music training. It's really quite amazing how some of these hearing areas get much bigger and stronger from early music training. And if you didn't get music training like me early on, it's going to be very difficult to get in adulthood, because some of those areas have died away. So the moral of this story is, the brain is plastic, it's moldable, and it gets molded by our experience, and practice and physical activity really matters for the developing brain. Okay. Developing brains are also very vulnerable, much more vulnerable than our adult brains. So, for example, the biggest cause of mental disability in childhood is fetal alcohol syndrome, and that's the drinking while pregnant. We do see mental and physical problems caused by that. Alcohol is going to decrease glutamate. Glutamate is a excitatory neurotransmitter, so neurons that are not getting excited are not getting those neurotropins, and therefore they're getting that apoptosis, and they're dying. We do see the same kinds of problems with smoking, cocaine during pregnancy, much greater chance of behavioral problems, psychological problems. Antidepressants you should not take while you're pregnant. Stressful experiences while you're pregnant can cause problems as well. So we do see that developing brains while pregnant are very vulnerable to a variety of different kinds of assaults. And that's why you're not allowed to take so many medications while you're pregnant. Okay, here's a great video. If you get a chance to look at it, please do. You guys have a great, oh, no, I'm not done yet. Okay, there's a test of impulsivity here. I'll do that in class. Okay, so as we talk about adolescence, we start to see still that we are getting some brain development in adolescence, and especially in the frontal lobe. So most of the brain is pretty well developed by adolescence, but still right up here in the prefrontal cortex, we're starting to see still some development happening there. And if you recall, the prefrontal cortex is involved in logic and decision making and all this stuff. So it's really no surprise that kids make a lot of weird decisions in terms of, getting having sex and with no birth control or no protection from disease, things like that. They have a bad inability to delay gratification. If they want something, they just do it a lot of times risky behaviors that adults don't do. That is because those areas of the brain are not fully developed yet. And we can do better even as teenagers. Teenagers that are given more time to think about a decision tend to make better decisions. But if it's a impulse decision, they just tend to make not so good ones because that part of their brain is just not too developed yet. Okay, well, we will continue on Objective 2 next time. I hope you guys have a great day and goodbye.